Hello, my name is Scott Grizzard. This from the University of South Florida. This is Calculus 1, Extra 6. I'm going to prove the chain rule. So this is the full proof of the chain rule, the big version. So let's look at it. Now, just to remind you, before I had this issue, in my earlier chain rule, I had this little piece where I had to make sure that g of t did not equal g of x for any t near x. And that was important because I can have this psychotic function here, okay, where that's not true. And I needed that because I wanted to cancel the change in u's. I wanted to be able to divide by the change in u, so I had to have the change in u not be zero. But there are psychotic functions out there that we might want to take derivatives of. I don't know why you would want to, but mathematicians are always like, oh, sure, if I can. This actually does meet the definition of the derivative. Let's go ahead and go through it. This psychotic function here is differentiable everywhere. Now, if I want to show that, let's prove it. So if x does not equal 0, I can just use the product and chain rule, okay? So if I was going to write the strategy, I would say something like this. So my strategy is that if x is not equal to 0, I'm just going to do it normally using the product and chain rule. But if x does equal 0, I need the h definition of the derivative and then two cops and a drunk. So this function is really psychotic. Let's look at the proof. Okay, so I'm going to let x not be 0. Then the derivative of g of x is the derivative of this version here, x squared times sine of 1 over x. I do a product rule, and then I'm going to have, because the outer layer of this thing is a product, I'm going to have a product rule. Then I'm going to take the derivative here using the power rule, but over here I've got a chain. I've got an x to the negative 1. I'm just going to call that u. And then I'm going to take the derivative of u with respect to u of sine of u times the derivative with respect to x of u. So that's just a chain, just like we did in the main lecture. So now I'm going to have 2x times the sine of 1 over x, that's all baggage now, plus x squared times cosine of u times the derivative with respect to x of x to the negative 1. Well, when I do this piece, baggage, but I sub back into u, I do this piece, I end up with a negative 1 using the power rule. I end up with a negative 1 in front, x to the negative 2. Now, that x to the negative 2 is going to cancel with that x squared. I'm going to wind up with 1 on each case. I bring over my negative 1 when I simplify, and I've got 2x sine of 1 over x minus cosine of 1 over x. And that's if x does not equal 0. If x does equal 0, I'm going to use the h definition of the derivative. I'm going to go ahead and sub in the 0 right away. I'm going to have the limit as h goes to 0 of g of 0 plus h minus g of 0, my x equals 0, all over h. Well, g of 0 is simply 0, according to my definition. So the only thing that's left is g of h over h. Well, g of h, because h does not equal 0, I'm near 0, is h squared sine of 1 over h. So I've got my h's are going to cancel. I'm going to be left with the limit as h goes to 0 of sine 1 over h. Remember that two cops thing that we did earlier? When I did this in class earlier, when it was x times sine of 1 over x. So now I'm going to let top be the absolute value of h, bot be the negative absolute value of h. This shows that I've actually trapped this thing, right? So negative 1 is less than or equal to sine of 1 over h is less than or equal to 1. Because of the range of sine, anything, I'm still going to be stuck between negative 1 and 1 when I do this. So if h is greater than 0, I don't flip the signs, and I get negative h is less than or equal to h is less times sine of 1 over h is less than or equal to h, and h is greater than 0, so this is negative absolute value of h, this is absolute value of h, right there, right? Negative h is negative absolute value of h if h is greater than 0, and if h is less than 0, I flip the signs, and I get negative h is greater than or equal to h sine of 1 over h is greater than or equal to h. And then again, because I'm less than 0, this negative h meets this definition. I'm sorry, this negative h means this definition, and this h meets this definition because I'm less than 0. So the first condition of 2 cops was met. Both of these functions are continuous, so I'm just going to ds both into them both. And I've got the second condition. Everyone's heading to 0. So by 2 cops, the limit as h goes to 0 of h sine of 1 over h equals 0. So g prime of 0 is 0. That means that g prime of 0 equals all of this. And I'm done with my proof. Now, notice something interesting about this piecewise function. It's actually not continuous. Here is a function that was differentiable and has a perfectly good derivative, but the derivative isn't continuous. And the reason the derivative isn't continuous is because this function here that doesn't have limits as x goes to 0. Okay? It's still a valid derivative, but it's not a continuous derivative. Okay? If you want the sequence to show this, plug in the sequence Sn equals 1 over pi n. Okay? So if I plug that in, I'm going to wind up with Sn equals this. But notice that this right here, when I do, right, 1 over n pi is just n pi. This term is going to equal 0 every time I've got 1 over pi n in it. Then I'm going to have the minus the cosine of n pi. That means I'm going to have 0 minus the cosine of n pi for every Sn. That means that Sn equals -1 if n is even and 1 if n is odd. That means I have got 2 sequences that don't converge, right? I've got 2 sequences in the y space, right? I've got that don't go to the same number. So let's look at that. That's this, right? Here's my sequence. I did Sn equal to 1 over pi n. There's my y equals g prime of x. And as you can see, this thing is just nuts, right? As I approach 0, this thing is just nuts. And there are my 2 sequences, the evens and the odds, or evens down here, odds up there, that show that this thing, those sequences in the x space are both heading to 0 in the x space. But in the y space, one of them heads to -1, the other one heads to 1. -1 and 1, they're not equal to each other. So I've got something without a limit. Okay, so let's prove the chain rule in all its glory. Okay, what I want to show, I already said this before, I want to show that the derivative of f of g of x is the same thing as f prime of g of x times g prime of x. So what am I going to do? I'm kind of going to do what I did before, except I have to not use a rabbit. I can't use a rabbit here. I've got to use a special kind of function. I've got to use a very, very, very different type of trick. It's very technical, what I'm going to do. But I've got to deal with this issue where the change in u equals 0. That's the whole point. Because remember from before what I did, right? Before, I had this kind of rabbit where I just multiplied by the change in u over the change in u. But if the change of u equals 0, if t and x, if t equals x near x, if g of t equals g of x near x, then I'm going to have a problem. So I had to make this assumption in my original proof that I didn't have that problem. Okay, so now what I want to do is I want to work around that problem by defining a new difference equation, something to take the place of change in y over change in u in my proof. And that's going to be what I did. I'm going to define this modified difference function, m of w, to deal with where t equals x. And then I have to show that it serves the same purpose as the original function. Okay? So the original piece. So what I'm going to do is I'm going to do a proof in stages. First, I'm going to define what this m of w is, and then I'm going to show the following 3 things. I'm going to show that this right here, which was change in y over change in u, right, times this piece, which is change in u over change in x, is still equal to my big change in y. So this right here in the original proof was change in y over change in x. So I have to show that my modified change in y over change in u still works for its purpose. And then I have to show that the limit of this thing here is f prime of g of x, right? Because that's what I wanted to show. I wanted to show that the limit of, that piece to become f prime of g of x. This piece will still become g prime of x. And then I'm just going to put it all together. So there's kind of steps that don't make sense unless you've watched the previous video to understand the previous proof. Okay, so let's put it together. First, we need to define what we've got. So what I'm going to do is I'm going to define the following difference function. M of w. Now, this w, I'm just creating a new w. So, don't be too worried about what that is. And I'm just going to let it be sort of the old thing if I'm okay. So I'm going to have f of w. Okay, so I'm going to have this kind of piecewise function. Now, notice that the x is fixed already. Okay, I should actually just say that x is already fixed. Okay, but so I already have an x. So this x here that I'm doing is independent of w. Notice that the only things that are going on here, okay, I've got an f of w here, that's dependent upon w. I've got a w here, that's dependent upon w. But notice if w equals g of x, in other words, this is going to become g of t later. If g of t equals g of x, I've got f prime already built in. I'm not going to allow that thing to just derail my whole bit. Okay. And this gives me a little bit more control about what's going on, which makes me a little bit happier. Okay. So now I've defined it. I need to show that this thing works. Okay. And there are two cases, either g of t equals g of x or not. Okay. Well, let's assume that g of t does equal g of x. So this is the case. If g of t equals g of x. Okay. Now, if that happens, this piece right here, I'm going to use this piece of the definition. I'm going to use the second part of the definition if g of t equals g of x, right? Because I'm subbing in m of g of t, right? So w equals g of t. And that's good. But if g of t equals g of x, notice that the second term here is actually 0. Okay. So this right-hand side here is actually going to equal 0. But notice what happens, I'm sorry, the left-hand side, but notice what happens to the right-hand side. The right-hand side goes to 0 too, because f of g of t is now f of g of x. They're equal to each other. Right? G of t equals g of x, so f g of t now equals f g of x. I'm evaluating the function at the same number. Well, I have another condition. I have another possibility. And that possibility is that they're not equal to each other. If that's the case, I'm going to use the first definition. I'm going to have f of w. Well, f of w is simply f of g of t, because I'm subbing it into this m business. And I've got this whole thing here. And that's okay because g of t doesn't equal g of x. Well, that's what m of gt, so now I'm going to multiply that by this other terms. I've got this term again, right? That was m of g of t, and now I'm multiplying by that term. Well, that's fine. This term here is going to, these two terms right here are going to cancel. And I'm left with what I want. Either way, I've shown that these two terms are equal. Right? It's true in either case. All right, the next thing I'm going to show is I want to show that if the limit as t goes to x of mg of t, I need to show that it exists because I really want to use the product law on it. And I also want to show that it's f prime of t. So if I just show this bit, if I just show this bit here, the bottom bit, I've actually also shown the top bit. I'm just mentioning it because it's there. Okay. All right, so let's see. How can we show that? Well, there are two cases. The same two cases we had before. So let's see what happens if g of t equals g of x. All right, so if g of t equals g of x, m of g of t simply equals f prime of g of x. Right, that's from the definition. Well, if that's true, notice that this term right here actually doesn't depend on the limit. This term right here totally does not depend on t. This right here is a constant as far as t is concerned. Okay, so I do the limit of the constant thing and I'm done with it. That's why I chose f prime of g of x to happen if the two things were equal. Okay, so let's suppose for a moment that they're not equal. This is going to look exactly like what I did before. Okay, the limit as t goes to x of m of g of t equals the limit as t goes to x, and I'm just going to sub in the old difference equation that I had before, right? So this one's m. So this is f of g of t minus f of g of x all over f of t, g of t minus g of x. Okay, so what I'm going to say here is I'm going to let u equal g of x, v equal g of t, the limit as t goes to x of v equals the limit as t goes to x of g of t. And this is going to equal g of x. Why? Why does that equal g of x? Well, it equals g of x because g is differentiable at x, making g continuous at x. Well, if g is continuous at x, that's the definition of continuity. Right? I can directly sub in. So that means this whole bit here equals the limit as, so v goes to u. That's what I just said. I said that v went to g of x, which equals u. I said v went to u as t goes to x. So I'm going to replace the t to x with a v to u. And then the top is going to become f of v minus f of u all over v minus u. And that right there is the v to u definition of the derivative of f. And now I actually have all the pieces I need. Okay. Now, I know it's a little, if you haven't seen the diet proof, this is going to be a little jarring. So I encourage you to watch the diet proof to understand what the little replacements I've done now. But now I have all of the pieces that I need to actually finish the proof. So what I want to do, this right here, this term right here, I should give a little bit more space. Right? This term right here is the exact same. This term right here is f prime of g of x. Okay. That's the t to x definition of f prime of g of x. So let's just write it out. Okay, so f prime of g of x equals the limit. It's not f prime of g of x. I'm sorry, that's fg prime of x. So fg prime of x equals, now I sub in the stuff I had before. I already showed that this piece right here equaled this piece right here. Okay, so now I'm going to use that piece right there. Okay, so now I'm going to split this up. I already showed that this piece, the limit exists, and I know that that limit exists because f is differentiable. That means I just apply the product rule. I'm sorry, the product law. This equality I already showed earlier. That was the point of the previous thing. And that's it. I've shown what I want to show. I have shown that f circ g prime of x equals f prime of g of x times g prime of x. And it was a proof in pieces. And the pieces themselves were, first I had to create this function that I had more control over than the weird functions that I could wind up with. Then I had to show it was equal to the parts I had before. So if you look at this part of the proof here, right here, and you compare it to this part of the diet proof, right? That was, instead of a rabbit, I now have an M. Okay? Instead of a rabbit, I'm now using an M here. And this piece still became what it became. This became my M. And I did that same trick before with the continuity to deal with the one piece that I had to deal with. And then I wound up with what I wanted. F prime of u times g prime of x, which is f prime of g of x times g prime of x. Okay. It was just the exact same thing, except I had to deal with this situation. So that's how you prove the chain rule in all its glory.